2 months ago, Turnstile made a presentation talking about machine-assisted proofs, and he made this remark.
Beginning to solve some simple problems in mathematics and or to assist with secondary tasks in a mathematical activity. So far, they are not good at directly solving hard math problems, but that may not be the best way to deploy them.
As if it was just a foreshadowing, this week we had AlphaEvolve. And yes, maybe just directly using LLMs to solve hard math problems was indeed not the best way to deploy them. We need something else. We needed evolution, as in evolve here. AlphaEvolve, the new Alpha series from DeepMind. As if the Nobel Prize was not enough, now they're going for the Fuse medal. And in this video, we are going to understand how this thing works, at least the details that they released. But let's also reflect a little bit on what this means for the future of science in general. Hello, people who watch my channel. Today we are discussing AlphaEvolve and scientific discovery done by agents. And for the name, it's part of the Alpha series. So you have AlphaGo, AlphaStar, AlphaFold, etc. And the evolve part tells us that this uses some kind of evolution algorithm, which is new, different from the other alpha models. It's not a model, actually. It's an agent. It's a coding agent that is designed to solve hard problems. And how does it do it? Using an evolutionary algorithm that heavily relies on an LLM. In this case, they use Gemini 2.0. And AlphaEvolve is going to be divided into 4 parts. We're going to have a prompt sampler, an LLM, a pool of evaluator functions, and a program database. You're going to see that the whole idea is not so complicated, actually. When the scientist comes, it's going to need to have some kind of code, some pre-existing code that tries to solve the problem and some kind of prompt explaining what that problem is. And then what the model is going to do, actually not one model, but several versions of that model in parallel, I'm going to try to generate several possible solutions for whatever that problem was specified. The solution is basically some updates to the code, a git diff, if you may. Next, it comes the evaluator code. And this code is very important. The scientist has to define the tests, the evaluation, how things are measured. At least here, they did not use any kind of LLM as a judge. And then finally, we get the results. And the results can be any kind of number, can be actually multiple metrics even, they say. And these metrics are added to this database, but it's not any database, it's an evolutionary database. So that's the rough overview of the first step. What happens in the next step then? In the next step, and that's where the evolutionary part enters, this database is not going to pick all the outputs that the model generated. It's going to pick the best ones based on some kind of evolutionary algorithm. Imagine that each metric works like a probability. The higher the metric, the higher the probability of it being picked. So if you asked it to optimize some code, let's say, maybe your evaluation could be the time it took. The less time each of the programs took to run as by the evaluator result, the higher the probability that they will go to the next step. And what happens in the next step? We do it again. So you can see that each step is just trying to improve whatever it did before, with a high likelihood of getting problems that were already closer to your goal. This idea here is not exactly novel, to be honest. They actually say this. Before AlphaEvolve, they had this other agent that was called FunSearch. But FunSearch was very limited. It used small LLMs. It only evolved a single function. It only run Python. It could only optimize a single metric. Whereas AlphaEvolve, they generalize. They really put the gas into it. What if we scale this thing massively? So instead of evolving a single function, what if we evolve a whole code base? And it makes sense because now you have LLMs that have millions of tokens in context length. So you can literally put a whole code base there. You can use any language because if they're using Gemini now, it can work with anything. And everything can run in parallel. So they really scaled things, I would say, both up and out. Google says that they have been applying the AlphaEvolve on their own things for at least a year. So it's not a surprise to me that in a recent paper from Alpha Geometry version 2, you've seen something similar. As you can see in the Alpha Geometry 2, they already have some kind of search algorithm that seems to use database and the symbolic engine that is deductive database arithmetic reasoning. So they've already been playing around with things like this. But the main point I think here is the fact that it's fully parallelized. And we have to understand this as a big novelty, actually. Oh, but parallelization is something that we all known for so long, right? How can it be novel? It's actually something they say in the paper. We've had, since DeepSeek R1 in the beginning of the year, been talking about test time compute, right? Scaling test time compute is a way of improving the output. But when people think about scaling test time compute, they only think about scaling up. As we've seen several papers like S1 simple test time scaling, they show that the longer the model is made to think, the better the result. But this is only scaling up. Scaling up in this, just like in regular software engineering, we put let's say a better model or make it work with more RAM or more resources. But what about scaling out? I'm talking about parallelization. What if instead of only increasing the length of the output, we also put several models to work in parallel on the same task? That's why they say that AlphaEvolve can also be seen as a test time compute agent, because its evolutionary procedure significantly enhances the capability of the base LLM. This is actually amazing, because we don't have to think about test time compute just in the sense of one LLM solving one problem. We can scale it out and put several of them. Only the best results. Just pick the best ones and keep improving on that. No learning algorithm and see test time compute evolution. This is, for me, the main point that I take from this technical report. And this massive parallelization, however, is also a big bottleneck. We can think that Google has the power of infinite money, infinite compute, right? However, it gives us a North Star of thinking about test time compute in a more broad way. And in the ablation sections, the evolution task in blue here is the one that seems to matter the most. And of course, it even depends on the problem itself. If you go to the full method, even with only 25% of the compute budget, it already solves the problem, basically. It doesn't get better than that. Whereas on the matrix multiplication that I mentioned, it seems to keep being able to get better. So maybe it would find even another solution if they put more budget to it. Who knows? And talking about compute budget, there are no precise numbers on this report on how long these things took and how much compute they are using. And this is where I think open source implementation of this will find several constraints. Maybe you can re-implement and apply this to some problems, but it will be very unlikely that the matrix multiplication problem they solved is going to be solved for cheap. The main point of this technique is the massive parallelization, everything about efficiency. For example, what if they added a reinforcement learning component to it? What if they got the results and used this as a reward to train the model again? That could work in theory, but then you could not make it so parallel, because the fact that it's so parallel and then basically use evolution is what makes this thing works, as you can see from the ablation itself. So we would have to rethink. I imagine that people would have to rethink part of this algorithm if they wanted to mix evolution with reinforcement learning. It might be possible, but I don't have the details. Maybe the people at DeepMind can figure it out. On this learning step, maybe the solution is already in the report itself, because they say that they consider distilling the AlphaEvolve augmented performance of the base LLMs into the next generation of the base models. So interesting. AlphaEvolve can uplift the next version of AlphaEvolve. Because it solves so hard problems, we can use these solutions that are completely novel to input the LLM again and train it and create a feedback loop, right? This is not a singularity yet. As they put in the conclusion, the gains are moderate and the feedback loops for improving the next version would be in the order of months. But beyond analyzing just what AlphaEvolve brings to the table, I think many papers are not only about what they are, but about what we will see coming. Actually, AlphaEvolve is just one step in a trend that has been happening for a while now. I'm talking about the trend of using AI to make scientific publications. So an AI made an agent called AI scientist and used to create a paper from scratch, all the ideas, all the plots, all the texts, not only the code, everything was made from scratch and it was submitted to a iClear workshop and it was accepted. However, they work differently from what AlphaEvolve does, but there are some similarities. AI Scientist V2 has an idea generation agent, let's call it that way. It has a tree-based experimentation part, which maybe that's where AlphaEvolve could even be used. And there's a paper write-up part, which is just amazing by itself as well. These three parts generate things completely from scratch. The user doesn't even need to input anything in this case. You can just say, make me a paper about whatever you want. It's probably going to be more tailored towards computer science or maybe mathematics, things like this. And most interesting, I think, the whole code is open source. Maybe I'm going to make a video trying this. I would really like, if it was just possible, for me to show them my code. Write this into a paper, whatever you think. Because the quality of the research, of course, it's not just having a random idea and publishing it. I would say the quality of a science is not measured by its answers, but by the impact of its questions. And those questions are still for humans to decide. So the way that I would use something like this is more explaining my research and just writing the paper. Because writing is fine nowadays, but if I could just not do it, if I could just tell an LLM, okay, so I did this experiment and make some plots like this, oh, it saved me so much time. In essence, it's a trend. People are really trying to get AI to do science, to solve science, as they say. I'll leave all these papers down in the description. And if you are also interested in other problems that require massive amount of computation like pre-training, check this video right here that I made last week. I'm trying to make videos every week now about the recent papers and things like this. I see you next week. Bye bye.